So we're back in 6.1. This is video number 3, and we're going to finish up one last example of an inverse Laplace transform. It's basically just getting a little bit more practice with the inverse Laplace transform. So what you notice right away is that we're taking the inverse Laplace transform of something that's kind of an ugly looking fraction. And we want to be able to simplify this. Our hope is that we can simplify this into something that is going to be the inverse Laplace of a simpler or several simpler functions of S, I guess you could say. So our game plan is to try to simplify this into several simpler functions. Now, if you're looking at this and thinking, I know how to simplify that, from Calc 2 we learned how to do partial fractions, and partial fractions might be the way to go. You're onto something. But the good news is that we don't want to take all of our time doing the partial fractions trick. You're welcome to if you wanted to. You basically would multiply the bottom, or think about the bottom as being two factors, and so you could split up the partial fractions into one fraction with a denominator of 3s plus 2, another fraction with a denominator of s plus 4. But Maple does this for us. And so what we can do is use Maple. And in Maple we can convert. This is going to be the code that you'd use. Convert, and then whatever it is that you want to put in there. And I'll just do this, your function of s, whenever it is here. And then you're going to say, I want you to parfrac, P-A-R-F-R-A-C, with respect to the variable s. So the code here is saying, I want you to convert this thing using the partial fractions trick with respect to the variable s. Now, if you type that into Maple, and I encourage you to do it, I've got it in the Maple worksheet for this video. You can take a look at what happens. Maple's really fast, super fast, and we find out that this thing is really equal to the Laplace inverse of the two fractions -7 over 5 times s plus 4 plus, the other one is 21 over 5 times, 3s plus 2. And again, I strongly encourage you to hop on Maple and just to try that out to see how it works. Because again, I'm not going to take Maple away from you and force you to do this by hand. You're welcome to if you want. It's just a really long process. So a little bit of effort, we can pull out our constant multiples here. This is -7/5 times the Laplace inverse of 1 over s plus 4 plus 21 over 5 times the Laplace inverse of 1 over 3s plus 2. Now we're really, really close to making sense of this. And this first one, you can probably tell using the table, that's just going to be e to the -4t. But this one is a little bit different. This one requires us to do a little bit of fancy footwork here. So I'm going to say, hold off on this guy for right now. We've got plenty of space on this page, so I'm not worried about it. This first one we know we can figure out. The second one, it's a little bit more complicated. Rather than, the table doesn't allow us to have a multiple in front of the s down here. So I'm going to have to pull the 3 out of there. Literally, I'm going to factor out 1/3 from this. So if I do that, if I factor out 1/3, then the Laplace inverse is now left on the inside. It's a little fancy, but the Laplace inverse on the inside is now 1 over s plus 2/3. So if you notice, if you multiply that 1/3 back through, the 3 distributes down on the bottom and you wind up with what you started with. So it's a little bit of fancy footwork. But now we're left with two inverse Laplaces that we can totally do just with our table. As a matter of fact, both of them are just exponentials. And they're negative exponentials in the exponent. So this becomes -7/5 times the inverse Laplace of all this is, I'm going to put it in a different color so it stands out. This would be e to the -4t plus, I'm going to multiply this together, 21/15 times the Laplace inverse of all this is e to the negative 2/3 t. Now notice, if I apply the inverse Laplace, then what I've just found is not a function of s anymore, it's now a function of t. So this is, you can think of this as being a function of t. We've just converted something that's in Laplace speak, right? This thing up here is in Laplace speak. We've just converted it back into the realm of the variable t. Now the same trick we're going to apply to the example that we started the last video with. So the very next page says, hey, well, what about that kind of sticking point that we were at, where we knew the Laplace transform of y was equal to this thing, but we didn't know where to go from there. So what we need to do is apply the inverse Laplace to the entire equation. So we can apply inverse Laplace to the entire equation. And when we do that, applying the inverse Laplace to the Laplace, it's like applying the antiderivative to the derivative. It kind of cancels itself out. And the other side is, well, it's just whatever the inverse Laplace of s minus 3 over s minus 1 times s plus 1, whatever that inverse Laplace is equal to. So this side sorts itself out. That's just y, well, and specifically y of t. The right-hand side, I have to use a little bit of fancy footwork, and so I'm going to use partial fractions. In Maple. And when I do that, I'm talking about finding the inverse Laplace of 2 over s plus 1 minus 1 over s minus 1. And again, you don't have to take my word for it. Hop into Maple, practice using the parfrac command, the convert, and then the thing you want to convert, comma, parfrac, comma, the variable, in this case s, and it'll split it up for you. And of course, we could ask Maple to just find the inverse Laplace of this. But one of the things that you'll run into is sometimes just applying the inverse Laplace right out of the gate doesn't work nearly as nice as breaking things up using partial fractions, because we want this to make sense to us. We want our solution to make sense. So after a little bit of algebraic manipulation, pull out the 2 in front, and we've got the inverse Laplace transform of 1 over s plus 1 minus the Laplace inverse of 1 over s minus 1. And both of those are pretty straightforward right in the table. We can figure that out. That's equal to 2 times e to the power negative 1 times t minus e to the power t. So what we've just found is the particular solution. Now, because remember, we included in our process, we included our initial condition. So since the initial condition was included in coming up with this Laplace inverse, or excuse me, this Laplace transform, when we apply the inverse, we actually wind up with the particular solution. So I'm going to end this here by saying this is the particular solution for our initial value problem. And specifically, that's our dE, which was dy dt. Oh boy, I'm going to have to flip back a couple of pages to remind myself. What was it? dy dt equals 4 minus, or sorry, equals y minus 4e to the, I think it's minus t? Yeah, minus t. Where y of 0 equals 1. That was our initial value problem. So that is the particular solution for that initial value problem. And I don't know if you paid attention, but we really didn't do any calculus. We applied our Laplace transform to this thing, including the initial condition. We manipulated our Laplace transform to solve for L of y, and then we inverted our Laplace transform. We found the inverse Laplace to turn it back into our a function of t. And so this is it. We only need to use the Laplace method if you have that initial condition. So note, I'm going to make a little note down underneath here, the Laplace method only really works if initial conditions are known. So if you don't know the initial conditions for your situation, then the Laplace method is going to be kind of stuck. And if I kind of flip back here a couple of pages to what we did to get our solution, if you remember when we were applying our initial condition right here, we would have been kind of stuck in the water. That just would have been stuck as a constant that I'd moved to the other side. So I just have to write like a C or a K there. You can technically use the Laplace transform method to solve things to get a general solution, but it's much, much harder to make sense of it after the fact. This method works great if you know your initial conditions. So down at the bottom of the page is a goofy little cartoon that I found online that I thought was cute. So from now on, when you hear things transform, you might have another way of considering transform, not just as a robot, but maybe as a Laplace. So that ends the video for the third video for this section. So that gets us through the notes for 6.1. We're going to start 6.2 in class tomorrow, and then we'll continue on with videos for that one as well.